Good evening. Please welcome Thomas Kleffel and Christian Daniel. The guys that brought you OpenTom will do this talk about DVB-T and how it works. Please welcome Thomas Kleffel.
Hello, everybody. Well, after TomTom, we had to do something new, and this year it's going to be our own DVB-T transmitter. So, well, we give you something to hack upon. Afterwards, well, this time we created something, and that's something somebody else can crack, nothing like the last year. The presentation or the lecture has 6 major topics. The first step is audio and video encoding. Then we will show you how the DVB packetizing works and what parts belong to a DVB stream. After that, Thomas will take over and explain the channel encoding and the modulation, which is the major part of our work. And after that, you will see, well, the realization, the hardware, which does the job. And finally, we will show you the Congress DVB-T transmitter setup, which is in place and working right now. Well, the picture is not perfect, but well, this is one of the few places, this room is one of the few places where the reception is not really good. Well, despite of the hacking center downstairs. Well, the signal path overview is here. It shows the stations the TV signal has to pass from the camera to the watcher's TV set. The first step, obviously, is the camera. The next step is the MPEG-2 encoder. We're using a hardware for that, well, which is not built by us. You can buy that for cheap. The next step is the multiplexer, which has to do, which has to combine all the streams coming in from the different encoders and make them form a DVB stream composed of several programs. So the idea behind DVB is better using of the channel bandwidth compared to the old analog TV system. And this is done by using the same bandwidth, frequency bandwidth, and putting more streams into that one channel. For that we need a multiplexer, and after that several additional data streams are inserted. It's the program service information tables, which tell the receiver what programs are in that stream and what the names are and who is broadcasting them and what needs to be done to receive them. After that, our work comes, the modulator. The modulator has the job to transform the bit stream into the radio frequency signal by breaking the packets up into bytes, and after that, adding error correction and then breaking it up into single bits and modulating them on the carrier signal. After that, the antenna comes, and that's where our responsibility ends. Receivers are cheap, and it doesn't make any sense to build them. Well, it makes sense, obviously, but not for us, since chips are really, really cheap, made by Chinese companies, so, no need to hack here. Well, the first step here is the demodulator, then the demultiplexer, and the demultiplexer also feeds the program service information table interpreter, which helps finding the programs, and the final step is the MPEG-2 video decoder, which does the decoding of the video and audio signals in the stream, and then, the TV set, which the watcher uses to, convert back to analog signal. So how does audio and video encoding work? This is this principal layout of the MPEG-2 video encoder. It's a predictive encoder, opposite the MPEG-1 encoder. The basic idea is that the receiver tries to guess the next picture based on information it already has. So, well, you only transmit the difference to that prediction. Everybody got that? Well, okay. Do it step by step. First, well, do you see the point? Yeah, works. Okay. Let's ignore this one. First step is to convert the picture into frequency components. What that really means, I'll show you on the next slide. Just accept that for once. Then data is reduced, which means an algorithm decides what data is not needed because we cannot recognize it. It's in the data, but we don't really see it or recognize it as information, and we don't experience a picture degradation by throwing away this data. Then after that, variable length encoding comes. This is something like PK-zip or something. Well, the algorithm is different, but it's what it does basically. And after that, the remaining data is packed into single packets. So what is the loop down there? It's everything in there what a receiver needs. So the quantization is reversed, then the picture is retransformed into picture data, and the motion compensator does one thing. It tries to detect movements in the picture. So you don't retransmit an area, but tell the receiver, well, there is a ball rolling, just copy the data from one edge of the picture to another, and don't retransmit the data itself. So this is done here. And after that, we have the prediction. So the encoder knows or needs to know what the receiver will predict. And after that, well, that's the first thing to do. We subtract the prediction from the actual picture that came in. For the first picture, we don't have a prediction, of course, so we subtract nothing, or zeros. And after that, we can count on the prediction and only transmit the changed data, which is most of the time not much. Well, you see me here talking, which means, well, my mouth moves, and we only need to update a small area of the picture. So the difference to the previous picture is really small. That's what the video encoding does. Okay, next to the audio encoding. Oh, slowly. This is what I promised to explain. It's the transformation into frequency components. On the left, we have the original pixel data coming in from the analog digital converter, and the block besides that shows the transformed data. So you see, this is some kind of gradient, and the transformed data mostly is 0. So the frequency components of this signal are really small, or, well, they're not small, but few, and you can compress this much better than this. This picture here has much more high-frequency components because it changes every pixel much more compared to the previous pixel. And the result is, well, it has more data in every frequency component, but still you can see how easy this would be to compress. So the idea is to transform the picture into the frequency domain and then do more efficient compression afterwards. Another thing that MPEG-2 video does is The predictive coding, which I told you earlier, it works in two directions. The stream is divided into groups of pictures. A group of pictures contains, well, an arbitrary number of pictures named, well, 10 or 12 pictures, half a second. And it starts with an iframe. The iframe is an intra-frame, and this frame doesn't use any data from any previous frame. So this is the first frame in a group of pictures with using the 0 picture as prediction. Yeah? Then we have several bidirectionally predictive frames. These use data from earlier frames and from later frames, which also tells us MPEG-2 doesn't transmit pictures in the order we are watching them. So every picture has a timestamp which tells the decoder when to display this picture. And, well, this order is different than the order the pictures are transmitted. Well, and the P frames, they're easier than the B frames. The P frames only use previous data as prediction. So, well, it's quite complicated. Most of us don't want to do this at home alone by coding that, well, using the standard as documentation. There's quite a funny thing. The standards only define how the data stream is decompressed. So how to compress it is your job to do. You can find an algorithm that works, or you can just encode interframes and don't do any prediction, but that blows the bandwidth usage. So, well, you better use all the standard features and write a lot of nasty code. Okay, audio coding. Audio is a bit easier to understand because it doesn't use any prediction. First step is the audio signal is divided into 32 subbands. That's a filter bank doing. And the subbands are coded independently. Alongside of the 32 subbands, 512 bands are analyzed. So you do 32 subbands for transmission and 512 subbands for analyzing the data or the signal. And then you decide what subbands need how much bandwidth to represent the original signal as much or as accurately as possible. Here the black magic box is the psychoacoustic model, which is much improved in MPEG-3. Well, MP3, you know it all. And, well, MP3 adds the prediction as well, like the video encoding. The quantization uses the information from the subbands and the analyzing results from the 512 bands to decide how to distribute the available bandwidth, and then afterwards the remaining data is just encoded into packets. Here in the voice prints, you can see what happens to the audio data when encoding is really rough. We have here an uncompressed audio data. This is the time axis. This is the frequency axis. And the the hue value of the pixels shows the intensity of this frequency. So we have here near silence and some, well, sounds in here. And after decoding, it's gained a lot of distortion. So 96 kilobits is a bit small for this kind of signal. We also see that we have a cutoff frequency here. The codec just throws away higher frequencies. Yeah, any questions to the encoding? Okay, then let's proceed with the packetizing. Again, let's have a look at what components generate the stream. We have for every program a video encoder, audio encoder, and a reference clock. The reference clock is needed to align the audio data to the pictures so that, well, the sound comes synchronous to the mouth movements. And, well, this takes a lot of, well, twitchery with data and clocks to have this synchronous and not have the speaker talk when he's silent again. Then, well, we have another channel. Here we have 2 audio encoders. This is, for example, on Arte, on Astra. They are doing a German and a French audio subcarrier. Pro7 does German stereo sound and AC3 surround sound. So we can just add an arbitrary number of audio streams. We have several multiplexers. One is inside every encoder, and we have the final multiplexer which does combine all the additional data, the PSI tables, the electronic program guide, perhaps some teletext channels, and, well, we can do IP data service as well. Well, in fact, we can add any data stream we have to this DVB signal stream or transport stream. This is the packet format. Every packet is 188 bytes long. Well, this seems to be quite a random number, but in fact it's not. It's 4 ATM frames if you count the ATM adaptation layer as well. This comes from the fact that most transmitters are not located at the studio where the stream is created, but somewhere on a hill or some on a mountain in the Alps, and you use a normal telephone carrier connection to transport the transport stream to the transmitter. And, well, using the ATM network for that is an obvious choice. So somebody thought this would be a good number. Every packet starts with the sync bytes 47 hex. This is everywhere. Well, you can think about how much bandwidth is lost in the sync bytes alone if you do some 10,000 packets per second. You can do a lot of things in that. But, you may not change the sync bytes because the receivers won't lock on the signal. A sad thing. Then we have the PID, the packet IDs, which help the demultiplexer to identify the original streams. Every original stream has a unique ID, and the demultiplexer just does comparing, or does compare the PID it wants to receive with the PID of a received packet, and if they match, the packet is passed on, otherwise the packet is just dropped. It's like the MAC address filter in your Ethernet card. Well, but it doesn't address the machine, it tells the receiver this is sound for program 3 or something like that. Then we have the clock reference field. It's not in every packet, but it's quite common or frequently transmitted, and it's needed to align the sound to the video signal. And after that, we have the payload, normally 184 bytes for each frame. This can be less if more header fields are added. The header contains a flag field which tells how many header fields are present, and then the header grows and the payload area gets smaller. And, well, the transport stream frame ends here, but the standard also allows 204 byte packets, and the last 16 bytes then carry the Reed-Solomon error correction code. This is needed to correct reception errors later on at the receiver side. Well, normally you don't receive these bytes. They are already used when you get the packet to work with it, used while compensating for reception errors, and then just cut off the packet. So next step, what data is inside the stream besides of video and audio signal? Well, mother of everything is the program allocation table. It has the PID 0, and from there the programs are referenced. So the first reference goes, well, to the network information table. This has a special meaning. And then every program has a program map table. Inside the program map table is a list of what streams belong to this program. Well, and obviously the PIDs needed to get in touch of these packets. So the program map table has a list telling the receiver, let's say Pro7 has video PID 101, audio PID 102, teletext something, and well, that's the list, and the receiver then lets you choose from several audio streams, perhaps, if the software does this. The network information table tells the receiver about the names of, or the name of the network, and well, several IDs, which help the receiver to, well, the idea is that the receiver has the chance to detect if you are watching the same program over several different channels, well, frequencies. So the receiver can say, well, Pro7, I know that one. I used to receive this on another channel, but now I update this program entry in the list. That's a lot of information in the network information table. Also, there is a list of other receivable frequencies. So here the idea is that a receiver that can receive the network information table can start spidering the channels without doing the long frequency scan. Just find the first one and then try the other ones referenced in the network information table. And then the stream also contains several tables which are not referenced but need to be there with fixed PIDs. The first is the service descriptor table. This carries the program names. Well, I don't know why the program names are not here in the program maps, but well, somebody decided that way. Then we have the event information table. The event information table isn't a table, it's a huge data stream carrying the electronic program guide. So why the electronic program guide isn't a distinct PID for every program, I don't know either. Doesn't make any sense to me, but well, we have to live with it. And then we have a rather easy table, that's the time definition table. It's just the time of the day in universal time coordinated. Well, DVB in binary isn't fun at all. It's got a lot of length bytes and attached data after that. So DVB mostly is one big buffer overflow. If you want to own a set-top box, it takes you 5 minutes, I guess. While writing the generator for the tables for the Congress TV, I just owned our test receiver. It crashed so hard we had to remove power. Switching on and off didn't work anymore. I guess most of the receivers out there are prone to hacks, so perhaps we now know what the next conference lecture will be. So yeah, it even gets better. Most set-top boxes support online firmware updates using the... Okay, fantasy is here, I know. Okay, Thomas, now it's your part. Thank you.
So, hello everyone. I'm going to talk about what happens to the data stream after being fed through the multiplexer into the modulator. The purpose of the modulator is to modulate the data stream onto a carrier wave. This is what has to be done to transmit it over the air. First thing, here is the block diagram of the modulator. There's lots of complicated stuff in there. I'll just go through some of them. Basically, the gray parts are the channel coding. There is some energy dispersal to generate a pseudo-random looking signal. This is needed for the HF signal having a nice spectrum. It's just to have a nice HF spectrum. You have several layers of error correction. There's a Reed-Solomon coder working on byte level, some interleavers. There's an FEC coder working on bit level. Those two match pretty well because the FEC coding works on bits and corrects errors which are randomly spread, also known as noise, and noise is known to happen pretty often in transmissions over the air, while the Reed-Solomon coder corrects block errors. For example, if someone walks by your antenna or a bird flies by your satellite dish or something, this is corrected by the Reed-Solomon coder. If there's snow on your satellite disk, which just adds noise, this is corrected by the FEC coder. There are some interleavers to spread errors around, but that's not too important. We need symbols, interleavers, constellation mappers. We will come to them soon. There's a Fourier transformation which does the OFDM modulation, which I will explain later. We have some filters which are needed on the HF part to prevent usage of the adjacent channels, because you probably only got one channel and you shouldn't disturb the others. Have I mentioned we will build a DECT hacking thing next year to shut the phones up? Sorry. Okay, so that's basically the block diagram of the modulator. Will come to modulation. For modulation, you need a carrier wave. This carrier wave probably looks something like this. It's a plain sine wave. And what you want to do is you want to impress information onto the sine wave. There are three ways to do that. The first way, the most basic one, is the amplitude modulation. It was basically invented more than 100 years ago, and it's still used today in Morse code, for example. Morse code is the most basic form of amplitude modulation. Just switch the transmitter off and on. Amplitude modulation uses intermediate steps, but that's what it does. Then there's frequency modulation. You can change the frequency of the carrier wave. It's also shown here. It's pretty intuitive. And the most unintuitive thing is phase modulation. You just change the phase of your carrier wave somewhere in between, which leads to some jumps in the time diagram. The interesting thing about that is that frequency modulation and phase modulation are correlated, so you can only use one of them. If you do frequency modulation, you also modulate the phase in some way. Otherwise, if you modulate the phase, you have to change the frequency. Other than that, the amplitude modulation is orthogonal to that. You can use amplitude modulation and frequency modulation on the same signal at the same time without disturbing each other, except in some special cases where the amplitude gets 0, but you don't want that. Okay, so here's what we do. If you choose to use phase and amplitude modulation, so you don't modulate the frequency, you can draw the wave you're currently transmitting on such a diagram. On that diagram, you draw the phase as an angel from 0 to 360 degrees, and you draw the amplitude as distance from the center. So you can express every carrier wave you might transmit as point somewhere in that plane. So if you build such a thing, a carrier wave generator, some box that magically phase modulates it, and some box that amplitude modulates that phase modulated carrier wave, you can transmit information. You transmit information by marking special points in that plane and say this could be 0, this could be 1. We have more points here, so we could 1, 2, 3, 4, 5, 6, 7, 8. So you could transmit 3 bits at a time with this constellation. Okay. Next step is choosing a scheme of modulation. There are simple schemes, for example, QPSK, which is quadrature phase shift keying, because only the phase is changed. If you look at the points, they're all in the same distance from the center. That means their amplitude is the same. I have also noted bit values in there, so you see how the mapping can be done. We have APSK, which is, for example, used in DVB-S2, the new upcoming DVB, which will probably someone bring HDTV to your home. And there is QAM, quadrature amplitude modulation, which is used currently in DVB-C and in DVB-T with some more tricks. QPSK is used for DVB-S. Just a note on the side is that normally you don't have separate amplitude and phase modulation. You do some pretty mathematical trickery called quadrature modulation to implement that, but that's not important for now. So if you can transmit a couple of bits onto such a system, such a symbol, the next question is how much symbols per second do you have? It means how many different points in that plane does the signal you're transmitting go to every second. This is called the symbol rate, because in, for example, QAM, 2 bits are called 1 symbol, and how often you transmit those 2 bits, this is the symbol rate. The symbol rate determines the spectrum. For example, if you look at DVB-C with 4,000 4 mega symbols, you get a bandwidth of 4.6 megahertz. You can see that here. If you switch up the symbol rate, you get more bandwidth, but broader spectrum. Okay, that's fine for now. DVB-S and DVB-C work like that, but there's a problem. We can't use that for DVB-T, that kind of modulation. Why is that? In an urban area, you got reflections. Your signal is reflected at houses, hills, whatever is there in your city. So what you're receiving is not an exact copy of the transmitted signal, but multiple copies with multiple different time delays. That's a problem, because on a typical DVB-S carrier, 1 symbol lasts only 30 nanoseconds. That's when you use 27.5 megasymbols, which is the common bit rate on such satellites. The symbols reaching the receiver with a detour of only 10 meters, 10 meters is not much if you have a house nearby or something, already overlap and interfere with the next symbol. The symbols are, if you imagine the symbols standing in the air, they are pretty short. It's only perhaps 1 meter, 30 centimeters in front of your satellite dish. The next signal, or the next symbol is there. So there are about 6 megabit in the air between a satellite and your satellite dish. If you have storage problems, just install some mirrors up there. Okay, data transmission in urban areas therefore only works with low symbol rates. For example, if you have GSM, which uses 270 kilosymbols per second, you need a detour of 1.1 kilometer to interfere with the next symbol. That's pretty much compared to the size of a normal GSM cell. The problem is that DVB-T cells are much larger, and DVB-T needs much more bandwidth than GSM. Another idea to increase bandwidth would be to use transmit more symbols in more bits in every symbol. We could, for example, do a quadrature amplitude modulation with 1024 points in there. But that's that isn't going to work because it gets more fragile to noise and to phase noise, and it simply won't work. So we need to do a trick. We need to decrease the symbol rate and increase bandwidth without increasing the fragility to amplitude and phase noise. This trick is called OFDM, orthogonal frequency division multiplex. This is a kind of modulation which uses a great number of narrow carriers. You remember, narrow carrier means low symbol rate. And with lots of narrow carriers with low symbol rate, we achieve a high bandwidth on small symbol rates. There's actually a trick in that. You have to put the single carriers in well-defined positions so that they are orthogonal to each other, which means they don't interfere. That's why it's called orthogonal frequency division multiplex. Luckily, there's an operation called fast Fourier transformation, which does that very efficient. So if we look at the spectrum, it just looks like that. You can see the single carriers. You just have to imagine in that 8 megahertz wide spectrum being 2,000 or 8,000 single carriers. It's quite a lot. That's the reason why OFDM hasn't been used yet. You can't do OFDM modulation analogically or in analog technique because you would need 2,000 separate modulators. You can't build that. So if you're using digital technology, you just put the stuff into the Fourier transformation and you're set up. So DVB-T is not the only thing using OFDM. We have VLAN, 52 carriers, DAB, digital audio broadcast, should be known to Britain people, up to 1,536 carriers, and DVB-T in its two modes, 2K mode and 8K modes, uses lots of carriers. So, how did we do this? Realization is where it gets really interesting. To do this modulation, you need lots of computing powers. There are three ways to get such computing power in our days. Either you buy a really big computer, but that's out of the question because it's just impractical, or you use a DSP, or you use an FPGA. We used an FPGA. For those of you who don't know what an FPGA is, there's a small introduction. Basically, the die looks like this. You have I/O blocks, which allow the FPGA to communicate with its environment through lots of pins. Most FPGAs have several hundred pins. Some of them even have more than 1,000 pins. So you've got plenty of bandwidth to communicate. In the FPGA, you have a switch matrix, which connects multiple function blocks, that are the big blocks, in a highly configurable fashion. It's actually even way more complicated than the picture here. There are lots of layers which do routing and stuff because that's pretty important. You have configurable logic blocks which can realize any possible logic functions on a couple of inputs. So 4 or 5 input logic functions can be just stored into that block. You also have memory blocks. Each of those memory blocks holds some few kilobits of very fast direct memory. Most of the time it's dual port memory. And you have DSP blocks, which contain multiplicators and accumulators, which is pretty important if you want to do filtering and stuff. Okay, so how does our DVB-T transmitter modulator look like? There's an overview. You have the transport stream, which comes from the modulator or multiplexer. It goes right into the FPGA, gets channel coded and OFDM modulated. There's even some HF stuff in there, the IQ modulation and up conversion to intermediate frequency. Then we go to a digital analog converter, which runs at 146 megahertz. Then you have some pretty little analog stuff, some filters and some amplifier. And then we go to the HF up converter, which up converts the signal to the transmission frequency, 482 megahertz in this case, adhere to 23C3, yes. Okay, there's some more filtering, and then you get the antenna. We also have microcontroller, some flash, front panel, RS-232, so things to play with. The board actually looks like this. Some of you might have seen it. I've shown it around for some time now. Let's have a look what's on there. First of all, we have a power supply. Power supply is pretty big because those chips need pretty much power and pretty clean power, so it's not too easy to build those power supplies. We have some microcontroller with 4 MB of flash. RAM is built in. We have RS-232, some connector for the front end stuff. Then there's the FPGA with its transport stream input. This is where the data gets in. It's directly connected. We have a clock generation for the FPGA. Clocks are pretty important in transmission and DVB-T applications. So there are 4 or 5 different clocks generated here with hopefully high precision. And then there's the DAC. It's a 14-bit DAC running at 146 megahertz. And as you can see, after the DAC, there's not much. There's only this filter, which cuts the bandwidth to 8 megahertz. This is made to make the people using the adjacent channels happy. And there's some amplifier. That's it. Everything done digital. So how does it look in... Oh, I marked this. Okay. So this is how it looks like. This is not complete yet. You need an up converter to push the signal up to the frequency you want to transmit on. You just put it on there, and that's it. There's a front panel for the board, which has some menu on it. You can set all the transmission parameters and everything. So it needs, but Linux needs to be somewhere in there. Because you want to do funky stuff with it. The FPGA, you can't, if you aren't too much into FPGAs, you can't do anything with that. You can't just use the software and turn it on and that's it. So we want to give people to play something to play with. That would be the Linux board. For that reason, we use the Centipede embedded Linux module. It features a 8091 RM9300 MCU, perhaps you know that. 64 megabytes of RAM, some flash, SD card slot, USB host and device. Device is pretty interesting in that case. Ethernet is even more interesting. We have some sound, RS-232, RS-485, some buses and stuff. Important here, this is also the reason why we choose this. We have the external data and address bus, which we connect to the FPGA. Another feature, it's pretty simple to use because it's breadboard compatible and you just need to attach 5 volts. So we built another board. This is pretty simple. You have a small FPGA sitting in there. You have a transport stream input, an output, and you can fit the Centipede module on there. It looks like this with the Centipede module fitted. And it boots Linux. And you can insert an SD card. And you have USB connectors, SPI transport stream connectors, some more connectors. And you can do funny stuff with it. You can insert and play with the PSI tables. That's where you would insert your the new firmware for your neighbor's DVB-T set-top box. You can generate EPG and teletext. You can do bit filtering and remapping. And you can stream in and out from and to Ethernet, USB, SD card. Pretty interesting. So, how does the setup at the in here look like? Don't be shocked now. This is what's upstairs. Yeah, but it's working, as you can see on the television. So every word I'm saying currently is running through that boxes and transmitted via DVB-T live. So this is basically some VPN box for the Ethernet port. We aren't crazy. This is a power amplifier. We borrowed that somewhere. And this is the box where our stuff sits in. So let's have a look in there. This is how it looks like. Don't be shocked. Hey, it was finished on Christmas. And we have nice stickers for the channels. Okay, let's have a look what's in there. One more. Yeah, we have a power supply, which is a standard power supply. Here are 4 MPEG encoders. You can only see 2 because the other 2 are under those. They are stacked. 4 MPEG encoders for 4 rooms. Those are hardware encoders from Fujitsu. You can see audio and video running in there. Between those MPEG encoders, below the cables, is the multiplexer. You can't see much of it, but it's not too interesting. It's just a small FPGA with lots of connectors, 4 connectors for the MPEG encoder, and 1 connector which runs to the Centipede module, which is here. It does the PSA table insertion and EPG insertion and malicious firmware playout and stuff. And from there we go in the modulator. This is the board we've seen for a moment ago. Then we have an up converter here. This is looking a bit different than the one on the other picture, but it's basically the same, but in a better quality. So that's what in the box that sits on top of the amplifier. It's not much, but it's a complete DVB-T transmitter. So you don't do such things alone. We have to thank some people for it, and we want to say who did it. We have Stefan Reimann, who also did the PR430 packet radio device for the ham radios. Probably someone knows this. He did hardware and HF design, PCB layout. We have Thorsten Schulze, who did the hardware integration and the system test. He also built the nice box with all the stuff in it. We have Bastian Euler, who built the MCU firmware. We have Thomas Seiler, who did the DVB multiplexer and the Linux kernel USB stack, I think. And yeah, we have ourselves who did the rest. Okay, what's on the radar? What's going on? Probably you've already noticed that all of this is work in progress. We finished in time for the Congress with the basic transmitter, but of course we are planning some things. This Centipede board together with that modulator is a generic software-defined transmitter platform. You have 150 megahertz DAC, can attach different up converters, stuff like that. And it would be suitable for DAB, DMB, DVB-H, ATSC, and all that broadcast-like stuff you probably know. We have currently a more powerful modulator in development. It uses a Vertex 4 FPGA instead of a Vertex 2 FPGA. So you can do more stuff and modulate several carriers at once or something like that. And perhaps the most interesting project is something we have in the planning stage, is a version with a receiver which can do OFDM, or not much of OFDM, but QPSK, QAM, GMSK, but it has a receiver, so it would be suitable as an amateur radio link transceiver or approaching DECT GSM. It wasn't a joke, remember? So that's it. Thank you. If you've got questions or comments, you can ask now or just call DVB-T. We have a vanity number, so just call us up. Thank you. Questions, comments?
Yes. Do you need a amateur radio license to operate this stuff, or how is this covered?
An amateur radio license is not enough for what we got here. We got a real TV license in here. It works on channel 22, so we asked for the license and we got it. It's pretty nice. What kind of license you need depends on where you are going to operate it. If you're doing amateur radio bands, you need an amateur radio license. If you're using broadcast bands, you need a broadcast license, and so on. If you're using some bands nobody will ask.
Well, the license for our work here can be seen on the picture with the, well, here. Okay, new PowerPoint. This is the license here. We just put it in there to find it if somebody wants to see it. Well, it cost 450 euros, so, well, a bit expensive for the Congress, 4 days. But it doesn't matter, you can have it for a year.
Yeah?
I think they had to look at your transceiver, so something of type approval. They don't want that?
That's probably right, but we told them we are using a self-built transceiver and they didn't object. And we have a channel filter here which cuts out almost everything that's outside of our band. It's a commercial filter. It's from an old analog TV repeater. Those are dismantled everywhere. So you can probably get them if you ask at your local TV broadcaster or something. And this prevents us from getting, from people asking questions.
Okay.
More questions? Yeah, there.
So I have 2 questions. The first one is how much does a hardware cost roughly? And the second is compared to your design, what do the television stations use currently, hardware-wise?
Okay, hardware cost is dependent on what you're going to use it for. For amateur use, it will probably be lower than for professional use. We have no prices yet, no fixed prices, so you might ask later, we don't know yet. But there are, of course, commercial products. This is, for example, a transmitter working on 2.4 gigahertz. It's a prototype. You can attach it to the back of a camera, like that one, and have your signal transmitted to that receiver, which could be in your broadcast car and doing live transmission to somewhere else. So there are, of course, commercial products, but there will also be hardware available for amateur use, and it will be significantly cheaper than the hardware for professional use.
As far as I recall, the price calculations for the amateur transmitter were below 1,000 euros. I can't promise it, but that's the price we aim for.
Okay. Second question? What was the second question again? Okay, he asked what the television stations are using. They're using, we don't know that. We know that it's way more expensive. It's coming from companies like Rode und Schwarz. And we think that they are probably using similar techniques. They use better chips with more performance, so they can do better filtering, but that's no problem. Some more questions?
Yeah. Would it be possible to reuse your design on a PCI card so that you could put it in
you don't need a PCI card. You can connect your PC via Ethernet. That's way more cool. Having PCI cards is a problem because there's noise inside the PC and stuff. Ethernet or USB is way more cool. More questions? Yeah?
Is there a maximum transmission power when it's in license free, like in embedded?
Yeah, it is, but it isn't for self-built devices. So, sorry, I repeat the questions. He asked if there's a maximum power where with that you can use the device for free. There is, but in some bands like 2400 megahertz, where, for example, VLAN operates, but it isn't for self-built devices. You need an amateur license to use self-built devices, but if you just use it in your house and you don't produce too much power, so you disturb no one will be able to take notice of it. So no problem. But you can fix that with an amateur radio license.
Nowadays, that's easy to get. Well, the most basic license, which allows you to transmit in the 2.4 gigahertz band, is, well, more or less buy it. No questions asked.
More questions?
How will you decide whether it's amateur use or commercial use? So, will you do it by the frequency?
For one reason, we will ask you what you're going to do with it, and for another reason, the amateur version will lack some features that amateurs don't have use for.
So, well, I can think there will be some people who would like to use it not to earn money, but on TV frequencies.
I don't know yet. We have to think about that. But if you don't earn money, it would probably fall under the amateur stuff. Amateur doesn't mean on amateur bands, but not making money.
And also, I think those people might like to buy it anonymously.
Again?
I think those people might like to buy it anonymously.
Yeah, we'll see.
Might be a bit off topic, but you've only talked about transmitting, but not receiving something. If I, for example, would like to emulate 802.11 device, I would also need to process some of these information, interact quite fast on that. Is this also on long term on the...
What do you want to receive?
For example, if I have a WLAN device, I have to react on acknowledgements, for example.
Yeah, that's done. You have to do that in the FPGA then, for the moment. But we'll see what we can do about real-time capabilities. Okay, I think we have to go now. And was denn? Yeah. Sorry? If there are any questions left, we are around, or call us on DVB-T. Thank you, bye.